This is section 7.2 on similar figures or similar polygons. So the first thing that you need to know about similar figures is up there at the top. Similar polygons or figures have the same shape but not the same size. So they have the same shape, meaning that they have all angles that are equal, but they're not the same size because their sides aren't equal. They're proportional instead, meaning that they have the same ratio. So if one side of one figure is half as long as the other one, then all of them have to be half as long as the other figure. So concept here says similar polygons. Two polygons are similar if and only if their corresponding angles are congruent. So the angles have to be equal, and the side lengths are proportional. Corresponding side lengths are proportional. That means when you divide their lengths, for every single set of for every single length of corresponding sides, those will be proportional. All right, so they show you the angles over there. A and W are congruent. They both have one arc. B and X are congruent. They both have two arcs. C and Y are congruent. They both have three arcs. And D and Z are both congruent. They have four arcs. For the sides, you have to compare corresponding sides. So you can see it says ABCD is similar to WXYZ. That means for side AB, the first two letters corresponds to WX, the first two letters of the other polygon. So that down here where it says corresponding sides, they put AB divided by WX. Then they make a fraction with the next two sides, BC, which is the second and the third letter in the similarity up there, and XY, which is, if you go to the other polygon, the second and the third letter. So we do BC over XY. They continue going around the circle, or around the polygon rather, CD divided by YZ, and DA divided by ZW. DA divided by ZW. And they're getting those from the statement where it says example in the diagram below. ABCD is similar to WXYZ. You just have to match up the letters in the first and second position with the letters in the first and second position. For the last one, they matched up the first and last letters, D and A, with the first and last letters from the other figure, Z and W, to get that. To get this 3 over 1, they just divided each side. AB is 15, WX is 5. 15 divided by 5 is 3 over 1. BC is 12. XY is 4. 12 divided by 4 reduces to 3 over 1. And they did that for every side. And if it doesn't work for one side, it doesn't work for any of them. They all have to be equal to 3 over 1. I'll show you a different way of doing this later. That works really quickly with triangles. Specifically, it works really well with triangles. The next section is specifically, section 7.3 will be on triangles only. So if you use my method, it will make next section quicker. All right. Here we have an example that goes over what we just talked about. If triangle FGH is similar, that little tilde means similar, to JKL, list all pairs of congruent angles and write a proportion that relates to corresponding sides. So use the similarity statement. The first letter is F from the first triangle, and the first letter is J from the second triangle, so F is congruent to J. The middle letter from the first triangle is G. The middle letter from the second triangle is K. G is congruent to K. And then match up the third letters, which are H and L. Those are congruent angles. The reason we know they are congruent is because it tells us, we know they're congruent because it says up here that the figures are similar. Remember, that's what the little tilde means. And similar figures have congruent angles. They have proportional sides. So again, just like in the first slide, FG are the first two letters. You put them on top of a fraction. JK are the first two letters from the second triangle. You put them on the bottom. Down here where it says proportion, FG over JK. They continue doing that with the second and the third letters, GH, and the other second and third letters, KL. Put those in a fraction. And then they do the first and the last, FH on top, and LJ on the bottom. And at this point, there's no numbers to check your answers, so you don't have to do anything else other than just write this stuff out. If you put the first triangle on top of all of the fractions, you have to do it for every single fraction. You can't mix and match. So if the FGH stuff goes on the top of the fraction, it has to go on the top of every fraction. If JK and L goes on the bottom, it has to go on the bottom every time. I have one more guided practice down here. You can look and read this. It says in the diagram, NPQR is similar to UVST. List all pairs of congruent angles. Write a proportion that relates the corresponding angles. It's just the same thing I did above. I just wanted you to have one more to look at. If you want to look at that, you can. If not, you can skip forward. You'll probably have to pause it to look at that. All right, on to the next thing. The ratio of the lengths of corresponding sides of two similar polygons is called the scale factor. We're going to be using scale factor all throughout Chapter 7, a little bit in Chapter 10, and then we'll use it a lot again in Chapter 9. So scale factor is going to be something we're going to be using pretty much all the way until we do the state test, more or less. So it's important that you know what scale factor means. The scale factor depends on the order of comparison. So if ABC is similar to XYZ, we compare side AB to XY, because AB are the first two letters from the first triangle, and XY are the first two letters from the second triangle. AB is 6, XY is 3, so you get 6 divided by 3, or 2. So if you're comparing the large triangle to the small triangle, you put the larger number on top and the smaller triangle on the bottom. 6 divided by 3 is 2, meaning the larger triangle is 2 times bigger than the smaller triangle. You can write it backward too. If you wanted to write it backward, you can do the 3 from the smaller triangle on top and the 6 from the larger triangle on the bottom. If you reduce those, you get 1/2, meaning that the small triangle is half as large as the large triangle. You can write it either way, but if you do it, make sure that you know which direction you're writing it. Are you going from large to small or from small to large? Because it actually does matter. You can't get your scale factor upside down. If the scale factor is larger than the number 1, then you're comparing the larger to the smaller. If it's less than the number 1, you're going from the smaller to the larger. And again, that's going to be important that you know about scale factor coming forward. So if you have any questions about this specific slide, obviously as it goes in your notes, be sure you ask me, because we're going to be doing scale factor in the next section. We're going to be doing scale factor all throughout chapters 9 and 10. All right, so on this one, this is kind of the longer problems, but again, it's not very hard. It says determine whether the triangles shown are similar. If so, write the similarity statement in scale factor. Explain your reason. So first you need to write down all of the congruent angles. I started in the top left corner here with N. N has 1 arc, so I went to the other triangle to find the other triangle's 1 arc angle, and that's R, so N is congruent to R. Then I did it again with Q and S, because Q has 2 arcs and S has 2 arcs, so Q is congruent to S. And then I went back to my left triangle. P has no arcs and T has no arcs, so P is congruent to T. Remember that you have to do this in order, so that if you do the larger of the 2 triangles first, you always have to start with that when you read them off. You can't skip back and forth from the larger to the smaller. Okay? Then you make these proportional sides. And the easiest way to make these proportional sides when you don't have this the similarity statement already written is find the smallest side from the biggest figure. QP is the smallest side from the biggest figure. That goes on top. Then on bottom, put the smallest side from the smallest figure. In this case, it's TS, which is 9.2. Then go back to the larger figure and find the medium side. In this case, it's 12.5. That's NQ. Then go to the other triangle, the small triangle, and you're going to put this one on the bottom. In this case, it's going to be RS. Then go back to the large triangle. When you go back to the large triangle, find the largest side, in this case NP, and then on the bottom of that, you're going to have the largest side from the small triangle, which is RT. If you do it this way, you will pretty much always get the answer right. There's a chance you can make a mistake, but if you do it this way, as long as you go from left to right, then left to right, then left to right, and you do large over large, small over small, medium over medium, large over large, you're going to set it up correctly every time. Then you substitute in all of the numbers. QP is 11.5, NQ is 12.5, NP is 15, so the larger numbers are all on top for each fraction. TS is 9.2, RS is 10, RT is 12. All of those numbers are from the smaller triangle. They go on the bottom in ascending order. And then you cross multiply. And when you cross multiply, you do the first fraction times the second fraction. And then you do the second fraction times the third fraction. And if when you cross multiply, you get the same number for the first fraction when you cross from top left to bottom right, and then from bottom left to top right, then those two fractions are proportional. The second set of fractions doesn't have to match the first set of fractions, as you see here below. So the work for the first set, I took 11.5 at the top left and multiplied it times 10.5, or sorry, by 10 on the bottom right. And I'm only doing the first two fractions here. When I multiply 11.5 times 10, I get 115. And again, I'm not looking at the third fraction right now. Then I go to the bottom left, 9.2, and multiply it by the top right fraction, 12.5. That also gave me 115. Both of those answers are 115, so they are a match. That means they're proportional. If the other set are proportional, we have similar triangles. If they aren't proportional, then we don't, because you have to have congruent angles, proportional sides. Okay, this is kind of like doing proofs for similarity. You don't have to write out the steps. You just have to show all of your work to prove that it's true. The work for the second set, you go with the middle and the right, and you ignore the leftmost fraction. So in this case, the top left would be 12.5, and the bottom right would be 12. 12.5 times 12 is 150. And then you do the bottom left from the first fraction times the top right from the second fraction. 10 times 15 is 150. So we have all matching sets for the second set. We have matching numbers, so the second set are proportional. So since the first set was proportional, the second set was proportional, all of the sides are proportional. We already wrote up top that all the angles are congruent. Therefore, we can write the following similarity statement, which should be popping up in green up here. Similarity statement states triangle NQP is similar to triangle RST. And the reason why it's NQP is because when we wrote our angles down there, where it says congruent angles, we put N, then Q, then P on the left. So we had to rewrite it in the exact same order. N, then Q, then P. And then on the right side, R, then S, then T, because that's the order they're listed where it says congruent angles. So we have to do it that way. If you don't do it that way, then you're wrong. All right, we got one more theorem and one more example. I know it's a little bit of a longer video, but obviously I won't be here for a couple days. So this is the last slide that you must have down in your notes. I think there were 3 total slides. So perimeters of similar polygons. If 2 polygons are similar, then their perimeters are proportional to their scale factor between them. My suggestion is just copy this down, and there's going to be 2 examples. The first example I'm not going to explain because I do it in a different way than the book. So just watch the example and hopefully you'll understand from the example. Copy down this theorem. Watch not the next example, but the example after that. I'm going to flash up an example for 10 seconds, not really going to talk. You can pause it and look at this example. That example should have just come up on the screen. Just the top part of it down to where it says, so the perimeter is 22.5. All right. If you want, again, pause it. I'm getting ready to go on to my explanation, but there is the explanation that the book gave. So I did guided practice 4, the problem at the bottom, and here it is. If MNPQ is similar to X, Y, Z, W, find the scale factor and the perimeter of each polygon. So Wx on the left side corresponds to MQ, and we know that from the similarity statement in the question, because Wx are the first and last letters, and M and Q are the first and last letters. Wx is the only thing with a number on it, so we have to use Wx. We can't use anything else because they're all blank. We're comparing Wx to MQ. I'm doing small to large. You can also do large to small. It doesn't matter. So in this case, I'm doing the small side 4, comparing it to MQ, the large size 8, which reduces to 1/2. So the scale factor is 1/2. Then we're going to find the perimeter of the figure that we can do for the perimeter. So in this case, the large figure, the large quadrilateral, you can add up all the sides to find the perimeter. The left side figure, we can't do it, which is why we have to do the right side. So 7 plus 8 plus 9 plus 10 is 34. That theorem says that if you know the perimeter of one figure and you know the scale factor, you just multiply those together to get the perimeter of the other figure. We know the scale factor is 1/2. The large figure is 34 units around, so 34 times 1/2 is 17. So even though we don't know any of the sides of that smaller figure, we know the perimeter is 17 units. It's actually pretty interesting and can save a lot of work for any field like landscaping or architecture that needs to do this. It's actually very quick and very nice. So again, find the scale factor by comparing the two sides and reducing the fraction that those two sides that you know make. So Wx and MQ in this specific problem. And again, we knew it had to be MQ with Wx because W and X were the first and last points on the similarity statement in the problem, and M and Q are the first and last points from the similarity statement up there. We reduced those to 1/2, found the perimeter of the larger figure by adding up all the sides to get 34, multiplied the scale factor times the perimeter. 1/2 times 34 is 17, so the perimeter of the figure we don't know is 17. Again, I will see you guys probably Wednesday or Thursday. Wednesday for Google Meet, Thursday for class next week. So please watch this and attempt the worksheet that whoever is subbing for me will hand out on Monday. And just do your best job, and we'll talk about it whatever is going on when I get back. So thank you for watching this video. I know it's pretty long, but this would be like a full 45 minutes of notes if I was at school. So you saved a little bit of time. You probably have to go back and look at a little bit of this. But again, thanks for watching, and I'll see you next week. Thanks.